Thanks everyone for coming to my talk today. Sorry I couldn't be there in person, but I hope this recording will do. I'm here to talk to you about trace elements in minerals that indicate nickel sulfide deposits. So this wasn't a solo effort, obviously. We had a large research team here at CSIRO that was working on this project, and as well as a bunch of industry sponsors, which are all listed on the screen here. So I'd like to take this opportunity to thank all of these people and all of these sponsors for making this project happen. So nickel is a very important metal for our green energy future. Everyone wants an electric vehicle currently, and within the electric vehicle rechargeable battery there is 29 kilograms of nickel. So that's one electric vehicle and one battery. So to meet this increasing demand for nickel, we need to find more nickel deposits. So to do that, we need to find new ways to explore under covered terrain. So nickel can be found in magmatic sulfide deposits. These sulfide deposits are formed when a mafic or ultramafic magma is saturated in sulfur. It then interacts with the mafic and ultramafic magma to enrich these little immiscible sulfide liquid droplets with metals. And then all of these droplets drop out of solution and are deposited in an accumulation or our mineral deposit. So our indicator minerals hopefully will tell us a little bit about one of these three formation components happening in our system. Indicator minerals can be resistate in nature. This means that they survive. Weathering and transport are usually found at the surface, but can be found in transported sediment above mineral deposits as well. And they give you clues to what resources might be nearby, and usually can act as some sort of vector back toward the mineral deposit. We are not looking at just indicator minerals at the surface, but also indicator minerals that can be within regolith profiles or within covered transported sediment terrains as well. Indicator minerals can also be in situ, where if you drill into an intrusion or a komatiitic flow, these minerals can tell us whether or not the intrusion that you've hit is likely mineralized or unmineralized. So this project, we wanted to look at a new way to use indicator minerals. We're not looking at just the presence and absence of minerals alone, but we're also looking at the trace element concentrations within these minerals and how they can tell you whether or not there's a sulfide deposit nearby. So the project that tested this theory had 12 detailed case studies from throughout Western Australia, which included komatiitic hosted nickel deposits, intrusion hosted nickel deposits, barren rocks, of course, to have our baseline. We also looked at a lateritic nickel deposit, some greenfield exploration zones, and world-renowned nickel deposits throughout the world. We ended up with 1,150 samples to analyze in this project. We looked at many different minerals as potential indicators for magmatic sulfide deposits. I don't have time, obviously, to go through all of them here today, but over the next year, they should all come out as little publications if you keep watching this space. The analysis we undertook was TEMA, so automated mineralogy on the SEM, in which we can aggregate spectra across a mineral and have semi-quantitative major element chemistry extracted from that data. And then we also looked at laser ablation ICP-MS analysis for the trace elements. We also looked at XRF mapping to look at zoning of elements throughout mineral grains as well. So in the end, we ended up with over 100,000 individual EDS major element spectra for these minerals, and over 18,000 laser ablation ICP-MS analysis for these minerals as well. So because we have an extremely large, robust and consistent data set, it's perfect for machine learning applications. We broke our data set into training and testing sets, ensuring that anything that was in our testing set, any sample that was in our testing set, any analysis from any mineral in any sample that was in our testing set wasn't also in the training data set, so that the machine learning model couldn't find shortcuts between recognizing a single sample and coming up with the answer from that. So we ended up using random forest models, and the best way to visualize whether or not these models is working is to compare the true classification, which is on the y-axis, with the predicted classification, which is on the x-axis. If the model was a completely 100% accurate, we would have ones in the diagonal dark blue, but you can see that we do have some false categorizing from the machine learning model as well. So this gives you an idea of how accurate the machine learning model is, and gives you an idea of whether or not you can expect some false negatives or some false positives when using these machine learning models. So after running the machine learning models, we can see what elements are being used to make these predictions and whether or not they make geological sense. So the first mineral and the main mineral we focused on in this study was spinel. We ended up with 42,000 EDS analysis of spinel. Most of them focused in the chromite field and many in the magnetite field. So looking at the major elements of these spinels, comparing them to the Barnes and Roeder fields that were published back in 2001, we can see that they are in very good agreement. So the komatiites exist in the komatiitic field, as was defined by Barnes and Roeder, and our layered intrusions, our small mafic intrusions and layered intrusions fit very nicely on the layered intrusion model from Barnes and Roeder as well. So this lets us know that if we found a spinel ex situ and measured the major elements, we could have an okay idea of what the host rock species was. So moving on to trace elements, we can see in our little confusion matrix down in the bottom that the machine learning model does a really good job at giving accurate predictions of whether or not the system is mineralized. This means that if we picked up a spinel ex situ on the surface or in transported cover, we could analyze it with the laser ablation ICP-MS and understand whether or not it's likely from a mineralized deposit or an unmineralized deposit. We also measured the volume of sulfide in each sample, and the machine learning models were actually able to predict the amount of sulfide in each sample. So using the trace elements in a chromite grain, we could make an assumption as to how much sulfide was associated with that grain at a sample scale. So this needs a little bit more work, but it is a really good indicator that these spinels are telling us something about the sulfide saturation process. So using this data we collected, we can turn toward other sources of TEMA or laser data and use these machine learning models to make a comment about the prospectivity for nickel in areas. So what we're looking at on the screen is the heavy mineral map of Australia that was published by Geoscience Australia and Curtin University late last year. And this is all TEMA data, so I was able to have access to the TEMA data, extract all of the major element quantification of the spinel and run it through the machine learning models, which gives us an indication of whether or not the spinel was associated with a mineralized intrusion. So what we're looking at on the screen on the right is each of those spinel analysis from the heavy mineral map of Australia overlaid over the nickel occurrences in Western Australia. You can see that the Kalgoorlie province has quite high levels of mineralized spinel. So the more red the spinel, the more proportion of mineralized spinel. The larger the circle means there was more spinel analysis. So you can see that up in northern Western Australia, these nickel occurrences are highlighted by these mineralized spinel analysis, and even the most recent discovery down in Julimar is also highlighted by mineralized spinel analysis. And a lot of the Kalgoorlie region also has these high nickel prospectivity analysis. So the next place I would look is probably over here near Coral Bay for the next nickel deposit. So the heavy mineral map of Australia was taken from surface samples, stream sediment samples. However, indicated minerals can also be found in transported cover above nickel deposits using previous paleotopography to understand the prospectivity under deep cover. So the second mineral I'll talk about today is pyroxene. We've published 2 papers on the use of pyroxene as an indicator mineral, which you can get to using these QR codes on the screen. And pyroxene is analysed using XRF technologies to understand the zoning patterns of chromium and titanium. So we found that complexly zoned pyroxenes, so the intragreen zoning of chromium in these pyroxenes indicates a conduit style system. Because of all of the flow through and flow back in these conduit systems, they incorporate a lot of wall rock, which melts, changes the chemistry of the magma, which is reflected in these changes in chromium content in the pyroxene. So although this isn't an indicator of sulfide saturation, it would be an indicator of potentially high metal enrichment, because if sulfide existed in these conduit systems, they would have the opportunity to interact with a large volume of sulfide liquid, a large volume of silicate liquid. So we found these zoning patterns up to 150 meters away from the primary magmatic sulfide deposit, which suggests that they could be used as a vector toward more active, more dynamic systems as well. And we also found that it was able to survive partial alteration to amphibole, where we can see these relic zoning, which is taken up by the content, the chromium content of the amphibole, and some exolved spinel. But however, when the amphibole alteration completely progresses, you can see that this zonation pattern is lost, unfortunately. But it does survive partial alteration, which means that it could be useful in minor altered terrains. So if we have zoned pyroxenes, we probably have a dynamic system, which means that we could have metal-rich sulfides if the system is sulfide saturated. This is mostly going to be an in situ indicator, which means that you need to drill into the intrusion, find some drill core, and have it analyzed by an XRF mapper. However, we have also found some zoned pyroxene in glacial till, so it does have some potential for being an ex situ indicator as well. So this wasn't a lot of time, unfortunately, to go into details of what we've done, but if you watch our website, you can be updated in all of the future of using indicator minerals to explore for these and other deposits in the future. So thank you for your attention, and if you have any questions, please feel free to reach out and email me. Thank you.